director of the Center of Biostatistics, Informatics, and Data Science at the MedStar Health Research Institute. She's an associate professor of medicine at the Georgetown University School of Medicine and director of biostatistics, epidemiology, and research design core, and a co-director of the biomedical informatics core at the Georgetown Howard University Center for Clinical and Translational Science. She's a very seasoned biostatistician, served as a principal investigator for more than 18 years and leading federal and industry-funded projects. And I know just from talking with Dr. Weissman, he's telling me in the entire system, you are the go-to person for machine learning. So I'm really happy to have the chance to have you here and for you to talk to us about informatics and machine learning a little bit more. But whenever you're ready, Dr. Shara, please feel free to take the floor and I'll listen in.
Fantastic. And we have Ross also, all good. Ross, you would like me to go first? You'd like to go first if you have time limitation? I'm going to be here until 1. What's your preference?
No real preference. No, go ahead if you'd like to. Yeah.
All right. All right. Well, thank you for the invitation. I will go first. Let me share my slides and I'm going to make it very informal. This is really intended to share with you what I have been doing in the past couple of years. And the thing about me is that there's nothing that scares me. So I will jump into anything in anything, technology, be it or AI or whatever. And so I started dabbling in this in 2017 when AI was not a big thing in at least in research. And I, collaborated, and my background is in applied statistics. And so this came natural. Machine learning, it's nothing other than fancy statistics, the linear algebra, the calculus, the everything we have covered in school. It's just, the computational power that we live in right now enabled these fascinating machine learning algorithms and solutions to take place in healthcare. So I will talk a little bit about a couple of things that would help you engage in the discussion, in the decision making, in learning. And one of them is the Aim Ahead, which I'm part of, and I have more information about it. You can feel free to take the picture of the barcode and sign up later on. But basically, as I mentioned, my background is in applied statistics. I head the department of the Center for Biostats, Informatics, and Data Science with my colleague, Dr. Hettinger. Zach, have you met before? I think he was the first presenter for your group, if I'm not mistaken.
But I don't mind if I have this playing.
All right. So basically, I wanted to just give you a quick display of the department so that you are aware of the resources that are out there. And as a medical student and later as a practitioner, what do you need to be able to do research? And nowadays for machine learning and artificial intelligence, anything like that, you really need to identify the infrastructure that is conducive to do these types of things, including technology, skill sets, the people you work with, the questions you may ask, all of that. So we provide the whole continuum of services for any research, clinical translational research that takes place across MedStar, not just ML powered or AI powered, anything that you can think of, developing databases to capture data, doing sample size calculation, doing review papers, write papers, abstracts, grants, etc., etc. So all of that's happening at CBIDS in my shop. Oops, how did that happen? And so as you see from this picture, data is everything for what we do. As a trained statistician, if there's no data, there's no job for me. And so everything that I do is surrounding data. And recently, everybody's talking about AI and machine learning, and they go hand in hand. But I like to think about it as AI being the bigger umbrella and machine learning, everything else comes underneath it. And it doesn't matter what it is. It's basically, anything that mimics human intelligence. So the Industrial Revolution replaced the muscular, aspect of humans. And now this revolution will replace the cognitive power of the human. And so it's the intersection between math, science, computer science, and business knowledge, as you see here on this slide. And so applications of ML in healthcare can be summarized as follows. And I'll show a couple of projects that we have done at MedStar, but I wanted to give this slide to give you an idea of the challenges. As someone like me with, the ability to do research, what do I need to do or know about the challenges that I may encounter in developing studies and going out? So the data is first and foremost the most important aspect of any project we want to do, whether it exists or we want to collect. It's always a challenge. And so the 4 V's, if you are aware of them, the velocity, the veracity, and the volume, and all of that, and the variety of the data continues to be a predicament in launching projects quickly and so forth. And one thing to keep in mind is that ML and AI tools that are out there require clean data. You have to clean the data and make it useful or usable by these tools. And so I have worked with the diagram that you have seen next, the second one here. This was MedStar's sources of electronic health records, admin and clinical and all kinds of things. And 10 years ago, this is what I was presented with to do research. And as you can see, I almost have a heart attack looking at this diagram of data sources and how do we, identify where to go for what types of data. And so over time, we kind of streamlined and identified the major sources of data that could be used to power these studies. And the computational power was another challenge in the past, not until recently. And even now, we are faced with computational challenges that require us to look for solutions, just as you see here in front of you, innovation, cloud computing, for example, the workbenches that are provided by Google and AWS, CPUs versus GPUs versus DPUs, and when to use what and for what purpose and so forth. So innovation, helped us come up with solutions to many of the challenges that we have encountered in the past. So what are some of the AI-powered solutions? So these are just examples of 3 projects that I have gotten funded from NIH actually to do research. And you can scan the bars and get the papers if you like, but I'll go into details of some of these. This is the simplest project that I have done many years ago where, I was presented by a problem where patients that are being seen at MedStar have 2 questions to answer when they leave. What did you like most? What did you not like most? And then we, administration wanted to make sense. So we applied Python and we quantified the negative answers. And as you can see, the most, the first category here is empathy or lack of eye contact or things like that. That was the #1 complaint by almost all of the patients who actually took the time to fill out one of the negative comments. So this is where it's, I started, bringing in new ways to look at unstructured data and not your typical structured EHR and so forth. And that was very useful, in my opinion, to make changes in the organization. Other studies where we applied random forest models to large amounts of data from the electronic health records. This was industry funded, and we worked with our clinical decision support, and we worked with our engineers to program this ML algorithm to identify the combinations or the phenotypes that would predict amyloid, transthyretin, wild type, cardiomyopathy in heart failure patients, this trait that would put them at a higher risk. And if we identify them early on, they can go through a process of treatment or of further, diagnostics to, figure out whether they can benefit from this particular drug or not. And so we did this and we published with our partners. This was a multi-site center, and the power of the tool basically was worth every minute we spend doing this. Our cardiologists are in love with this ML tool. They want us to implement in the AHR. And as you can see, these are the combinations that were identified by MedStar. We compared this to other systems, and we are now in the process of applying this prospectively and identifying ways that could be used to prevent and help our patients. Additionally, this is also another NIH funded internally. We were interested in looking at pre-diabetics and look and see whether the onset of disease, the 3 years onset of disease for those who were pre-diabetic were predicted by certain variables. And we used a machine learning technique and looked at structured, unstructured, semi-structured, and all of that from our electronic health records. And we wanted to identify the 3-year type 2 diabetes risk for the pre-diabetics. We ended up with a sample of 5,000 patients, and we, as you can see here, these are the variables that we have used. And we applied multiple and compared multiple machine learning techniques, regularized logistic regression, support vector, k-nearest, and all of that. And eventually we picked the one that performed the best, which was the regularized logistic regression. And now we are in the process of doing this and applying deep learning based NLP that teases out pertinent information from clinical notes that improves our prediction beyond the what we have done in the past. So we found out that there are certain patterns in our providers in the way they speak to our white patients versus Black patients. And this paper will come out in the next few months. And that would not have been enabled without applications of machine learning, deep learning, NLP, and so forth. This is the power of these tools nowadays and how we apply them. This is an NIH NCAT study that I got in 2018. As I mentioned, I started a long time ago thinking about ways that we can incorporate AI and machine learning. And so basically the idea was to be able to leverage voice assistant devices to help our heart failure patients manage their day-to-day activities. And so we worked with a company that was specialized to develop avatars at the time to help us set up the cloud instance and set up the Alexas and all of that. And at the same time, I pitched to them the idea of having a third arm if they are interested in funding me, to do a third arm where patients are using avatars and not Alexa. And they agreed, and they gave me the money and the tablets and everything. And we did three arms, and we followed our patients for 90 days. We used the Ask skill kit or the Alexa skill kit, and we programmed Alexa to initiate the heart failure care survey. It went through a process, and we projected the data. So it was color coded. That was the innovative part of this. It was color coded, thereby the clinician and the nurse on the team can immediately figure out which patient need immediate attention. And so we did the avatar too, and we developed this avatar ourselves. We worked with the engineers and developed Tara. We called her Tara, and we created everything from scratch. And we did the study. And this is the data workflow for this particular study. And these are the questions. Each part was color coded differently. This is the data, and this is the dashboard. And as you can see, once you have a red answer, you can, we got pinged. My phone rang, the heart failure nurse phone rang. So we developed a way that we can connect patients and providers immediately, real time, such that actions can be taken. And so this is published, and we try to figure out engagement between the two tools. And I have 2 papers published. This is one, the other one is being processed as I am speaking. And I will end up, I know I'm 15 minutes into this, I will end up by telling you how can you get involved. So I am part of this big, huge $100 million grant from NIH. I'm the PI for MedStar. It's I am serving in the data science and training core for AIM Ahead. AIM Ahead stands for Artificial Intelligence to Advance Health in Underrepresented Minority Groups. And our ask is to leverage the tools and the technologies that are out there, engage with our communities and stakeholders to make a difference, to have, develop curriculums that could be embedded in the training, that could enhance their experience and improve their prospects for jobs in the future. And I have been putting this symposium, I'm the chair of this symposium. It's going to take place June 28th, 29th. And then there is a startup competition on June 30th, where if you have a company that you would like to pitch and you are looking for funding, you're looking for support, cloud credits, whatever, come to us. There's going to be lots of people who are attending. We have judges and so forth. And then what's most important for you as medical students is the workshops that I have been able to put together for the entire month of July. So this is just a quick glance at it. You can log online and see the different topics that we cover in this symposium. It's free as long as you meet the criteria for participating in the first 20 that can join these workshops. The rest of the participants can audit, but the first 20 can actually have an interactive experience with the presenter, with the workshop. All of it is virtual. All of this is free. Something like this would cost you thousands and thousands of dollars. Take advantage of this. It's available to you through us. Ask me further how you can be involved. I'm serving in a committee. I'm one of 30 people in the country who are putting the ethics in artificial intelligence in biomedicine. We're discussing this. We're going to meet in June and come up with some kind of a white paper or something that discusses, how to make sure that whatever we develop is ethical, is, free of bias. How can we improve trust in these tools? And how can we engage with our underrepresented minority groups? I came across amazing people when I was putting this symposium together, and this is one that stuck, and I would encourage you to check it out. It's an amazing idea. This person, Jan Althusser, is building an open access, not-for-profit one fact foundation where you can where you can help people around the world who don't have access to great resources, medical attention, and all of that, engage and support one another. So his information, feel free, is very approachable, can talk to anyone and everyone at any point in time. And finally, I put these together so that the discussion continues on how do we ensure we have a balance between, the explosion of technology that we're living in and maintaining the morality, the empathy, the trust, the ethics of the tools that we develop, and knowing that this can be an amazing, helpful tool. At the same time, it can be a weapon in our hands that is misused by many. So with that, I think I can stop.
Thank you so much, Dr. Shara. That was like a wonderful presentation, so many applications. I'll open the floor up to questions, and I have one or two. Does anyone have any questions? Okay, maybe I'll just start off. So one question I had, Dr. Shara, and we'll definitely share the symposium with our listserv too. So you talked a little bit about, natural language processing using EHR data. I don't know if you talked a little bit about imaging, but there's these different classes of data that you can impute to then apply an algorithm on top of. Could you talk about, how far, when you compare these different classes of data in terms of the translational bridge, meaning coming into the clinic, where are we with imaging versus NLP versus EHR data, just some sense of how these things are going to progress in the next decade or so.
So when I think about imaging, Ross Filice comes to mind. I don't do any imaging as of yet. I'm starting my first project as I'm talking to you, but there are not many people within the organization that are involved in this field. I think Ross is probably one of the first people who were in this space. I heard about what he does a long time ago, and I'm about to talk to him about this new imaging project. But we are behind compared to other places. If it's not for the few people who are actually doing what we are doing, there's not much going on. However, we're getting there. I think with people like Zach Hettinger and Raj and others within MHRI, we're getting there. We're trying to, in the research world, it's different than operations, right? And so it takes a long time to translate what we do in research into operations, unless there are people who are like Zach and Ross and others who are actually in both worlds and can do things faster than we can do. But we're getting there. We're one of few people who have aim ahead, and that's going to expose us to everything cutting edge in AI and machine learning that's happening from a medical, biomedical perspective. So we're working with the gurus in the field. I'm working with AWS on a daily basis, Google Labs, and all of those. And so we get to know the best of the best, and we're getting there. I'm trying to bring as much as I can, and I have a lot of information. Feel free to email me. I will send you whatever you need, because I'm just bombarded with the amount of information that I'm receiving every day from these grants and initiatives.
Yeah, no, it seems like you're an essential hub for so many physicians. That kind of segues to my next question. As a scientist, are there gaps in understanding that physicians have when it comes to machine learning and artificial intelligence and these advanced applications that you think you commonly see? Just because many of us, we may not be coding or we may not be involved technically in some of this work, but we will be seeing some of the applications. And like you mentioned, like I think there's a results section that you mentioned with like some questions and how you read the text or those different colors. So just generally, have you seen things that physicians should think about when we interpret, applications of machine learning?
That's an excellent question. So I've been with MedStar for a long time, and I can tell you that the people who made a difference, the doctors who made a difference, are the ones who were trained in informatics, because they not only understand the science, medicine, and the issues and the pain points and the gaps, they have the technical expertise to develop solutions. And so they took it immediately and developed solutions that helps their workflow, helps, solve a problem in healthcare. For you as a new generation, I think you don't need to be programmers, but you need to know how what do these tools do? What can, what problems can they solve? How can I improve my workflow? How can I improve my patient's experience by, alleviating some of the burden off of me, off of my patient, by, allowing the machines to take that part, the tedious, the redundancy, all of these are automation. I'm talking about above and beyond things like that. We're now looking at sentiment analysis. We're experiences of patients and the way they talk, the way they act. What do they post? How does it relate to their outcomes? Like, think about the amazing amount, the plethora of data that's out there, and think that there's nothing that you can do in the near future, given the computational power and the tools that we have access to. So learn, listen, there's so much that you can enhance your current knowledge by just listening to people who do things in AI, machine learning, in biomedicine. And I think the sky will be the limit for amazing people like you who are going to be our doctors in the future.
Thank you. Yeah, we're super excited, and I'll definitely share it. We have like 100 people on our listserv, so we'll definitely share the equity event and then those other two kind of sessions you mentioned. I'll transition now to Dr. Filice. I'll just briefly introduce you, Dr. Filice, and feel free to expand upon that. Dr. Ross Filice, he's an associate professor and the chief of imaging informatics at in the Department of Radiology at MedStar Georgetown University Hospital, as well as the chief of imaging informatics for the MedStar Medical Group Radiology. He is a director of the Georgetown Radiology Informatics Mini Fellowship. Sorry, give me 1 second. And also holds a position as a clinical informatics scientist in the National Center for Human Factors in Healthcare within the MedStar Institute for Innovation. Dr. Filice performs clinical and teaching duties as an attending physician in the abdominal imaging section at MedStar Georgetown University Hospital. And then just personally, whenever I talk to Dr. Weissman, I ask him about AI and machine learning, the first person he always asks me or tells me about is you, Dr. Filice. He always says, have you talked to Ross recently? So I'm really happy that you could join us today, and I'm really pleased that we all can learn from your talk.
Yeah, great. Thanks for the introduction. Let me know if you're having trouble with my screen or hearing me. But yeah, that introduction was great. And what I'm going to focus on today is artificial intelligence just in the medical imaging field, so more narrowly focused than all of healthcare. It's almost passe these days to include these kind of quotes at this point because they're so wildly incorrect, but it's kind of fun to dig this back up again. So especially because we've reached the threshold of when everyone is predicting radiologist demise. So this was back in 2016. Jeffrey Hinton, who is a very famous, very smart computer scientist and deep learning expert, you can read the quote for yourself. It's basically saying that radiology was going to be completely obsolete and we should stop training radiologists. Andrew Ng and other incredibly prestigious artificial intelligence researchers at Stanford and Eric Topol, who has been in the news a lot for COVID stuff, were saying the same things. And then I used to have this article pop up in my Google reminder every year so I could check and see if I still had a job, with Ezekiel Emanuel and this other guy, Dr. Obermeyer, who I don't know well. Basically the same thing. In the New England Journal wrote this article about what machine learning was going to do to medicine. This was in September of 2016, and you can read this also, but basically saying that radiologists and pathologists would be replaced. And so it's kind of nice to look back now, because now we're at 6 years out, and these are all predicting us to be dead by the year 2021. And it was funny to look back and see what a huge disconnect this was, because anyone in radiology in 2016 who had some sense of what artificial intelligence meant, and just as a bit of background, like I have a bachelor's in computer science. I took an artificial intelligence class learning about neural networks in 1997, I think. And so this is before this latest peak of, hype in artificial intelligence. And anyone who was in that, I mean, we kind of had to second guess ourselves because all these really famous people were saying we're all going to die, but it just made no sense to us because, and I think what it shows is that people, especially the folks that aren't trained as MDs, as incredibly intelligent as they are, they just really have no idea what it means to be a radiologist or even really a physician. And they just don't understand the complexity of what any of us do on a day-to-day basis, and so far, we've been proven right. I mean, artificial intelligence is starting to make some impact in radiology, but mostly to help us and assist us and make us better. And, I still have a lot of scans that I have to read every day. So this all came about. The reason this sort of peaked, this interest in artificial intelligence in radiology was, in my mind, largely related to the ImageNet competition. And I'm not sure if anyone's heard of this before. But basically, there was a PhD, a professor at Stanford who hosted a competition every year. And what they did is they collected a ton of just regular everyday images of like birds and trees and houses and cars or whatever. And they manually classified all of these into a bunch of different categories. I think it was like 20,000 different categories. So they would get down to like the species of a bird and like the species of different animals and all sorts of different things. And they had a competition every year, starting I think back in around 2010, where anyone could join and download all these images and try and create an algorithm that would classify all of them according to what the humans had said the classes would be. And this contest basically had to end at around 2016 because everyone got so good, including Jeffrey Hinton's group, that artificial intelligence algorithms were doing better than humans, like by a large margin. So and everyone, once they learned sort of modern image analysis techniques, everyone became so good that the contest was basically worthless and they just had to discontinue it. There's some other like versions of this contest that still exist, but this one is basically over. And the reason this impacted radiology, or looked like it might impact radiology, is because it turns out if you take the algorithms that work well on these everyday color 3-channel images and apply them to grayscale radiology images, with a little bit of tuning and adjustment, they work very well. And so people started to do that. They would take those and move them to radiology images, and they saw some really promising results. And so that's when some of those folks started predicting the demise of radiologists. So the first thing that everyone sort of thinks about is this idea of, what I consider like detection algorithms. So this is something where you would run this on a hand X-ray, for example, like this, or wrist X-rays, and you can have an algorithm that would try and find where the fractures are or not. And you can see here, there's little boxes around these fractures in the distal radius and distal ulna and a couple of different patients. And, these images obviously look great, and these are just anecdotal, but there are algorithms that do quite well. And these can be very helpful. I think, perhaps for radiologists, I mean, one problem here is you'll see a lot of these examples. Now, even for you as medical students, I would probably, pose that you could see these fractures pretty easily, right? And so no radiologist should be able to look at these images and not see the fractures. Now, maybe once in a while you're not paying attention or you're going through films too quickly, and this algorithm could help you by finding those. But I think one of the reasons why, when the results look so good, they didn't really translate necessarily to radiology or to radiologists, is that a lot of this stuff is pretty obvious to most people's eyes. Now, it could still be helpful, especially to pick up cases that you might miss for whatever reason. It could also be helpful for other clinicians potentially in the urgent care setting or ER, where maybe they aren't as experienced as looking at X-rays. So I don't mean to say that there can be a lot of value here, but I think that could be potentially one reason why there's a little less sort of impact than people expected. This type of thing also got translated to cross-sectional imaging. So here's an algorithm trying to detect brain bleeds. And again, these are pretty obvious bleeds, but there are some real value in doing this kind of detection, both at the time of interpretation and for other reasons, which I'll talk about in just a slide or two here. Other things here, so looking at brain bleeds, cervical spine fractures, free air in the abdomen, and fractures and free air on chest CTs. All of which are very important diagnoses and good things to pick up. And some of these are more subtle than others. And so there can be some real value to running these and having these arrows displayed at the time of interpretation, so we make sure we don't miss anything. But I think one thing that might be the most valuable, now this is just some image I took from the internet, but our day-to-day work, we sit down, we have a work list, and it has a bunch of different exams on it, and we have double-click those, and it launches images, and then we create a report and send those off. And so our work list looks a little bit different than this, but it's basically the same thing. There's a ton of different exams, and we have information about where they're coming from, what type of exam, and most importantly, what we do is we have information like the time when they were ordered, whether they were ordered stat or not, and where they came from. So like the ER, ICU, urgent care, outpatient, the floors, etc. And so the way we prioritize how we should read things is pretty crude, to be honest. So the most important exams, or the exams you try and look at first, are those that are from the ER, or the ICU, or urgent care, those that are ordered stat, and those that have been sitting around for a while. Because the thinking is that, if they were ordered 4 hours ago, and all other things being equal, something else comes in that was ordered a minute ago, it's probably worthwhile checking that exam that's been sitting around to make sure there's no problem to be addressed, right? But all those are pretty crude heuristics. There's all sorts of cases where if an exam has been sitting around for 4 hours, but a head CT comes in from the floor, which is ordinarily not treated as, as critical as some other sources, but that patient has a stroke or a bleed or whatever else, in a perfect scenario, we look at that one first, because that could actually be something that could be addressed. And similarly, lots of things get ordered stat, and not even inappropriately. I mean, they appropriately do, but there's a lot of cases that are stat that don't have pathology on them. Or take the head CT example. We get head CTs all the time from the ER, and quite appropriately so, for people who have headaches or stroke symptoms or other things, but probably 90% of those are normal. So if you have a list of 100 head CTs coming from all the different 10 hospitals at MedStar, it'd be really great if an artificial intelligence algorithm could tell you the ones that might have a bleed, right? So if you go back and look at these kind of algorithms are not going to be that useful at diagnosis, because any radiologist opens this is going to see the bleed in 2 seconds. But if you have 100 head CTs sitting on the list, and an algorithm can tell you which ones might have the bleed and pop those up to the top, then we'll be able to look at those sooner and address the critical elements of those scans and get those patients treated. So that's sort of the class of algorithms that people talk about when they talk about triage algorithms, or you'll see the FDA refer to them as CAD-T, like computer-assisted diagnosis with a little t for triage. And those, I think, could have incredible value, because we have a lot of trouble really knowing how to prioritize the exams we look at. This is another class that I think of. So we're actually using this in practice now, which is sort of exciting. It took us a while we did a lot of research in AI, but it took us a while to really deploy something for clinical use. And so this is a thyroid nodule. It's probably does not look super familiar to a lot of you, and that's okay. Ultrasound takes a little while to sort of become accustomed to, but it's a thyroid nodule, and we have 2 views. So we're looking at it transverse, as if we're slicing the thyroid this way, and then longitudinal, so slicing it this way. And the reason we look at thyroid nodules is, number one, there's a ton of them. Everyone gets thyroid nodules by the time they get a little bit older. And number two, there's a fairly high incidence of papillary thyroid cancer, which obviously we want to catch and treat because it's a very treatable cancer. The problem is it's very difficult. I mean, not very difficult, but there's a lot of overlap in how benign nodules look and cancers look in thyroid ultrasounds. And so we have trouble figuring it out, and we end up referring a lot of patients to get biopsies, a lot of which turn out to be negative. And because of the high volume of nodules and cancers that we see, anything we can get to help us do a better job of that is super helpful. And so this, and there some societies have helped with that. So the American College of Radiology has a very formulaic way to interpret thyroid nodules that does make us better and certainly more consistent. But this company created an algorithm where you can bring up the thyroid nodule like this. You draw 2 little bounding boxes over where the nodule is, and then it will analyze it and give you an interpretation based on the ACR TIRADS, or that formulaic interpretation I talked about. And so here you can see it has gone through the 5 different categories of whether the thing is solid or hypoechoic and a bunch of other stuff. It will actually give you an additional piece of interpretation that it thinks how malignant the nodule looks like, and that's based on all of the hundreds of thousands of training images that it saw when it was being developed. And then you can model, and it'll give you the total score about how suspicious it looks and whether you should consider an FNA. And we as radiologists can adjust any of those if we think something was wrong. But when we did, so I participated in a clinical trial to get this cleared for the FDA. And when we did it, there was 15 of us that read all these ultrasounds. We read 650 of them, both with and without this artificial intelligence tool. And we did quite well when we did it alone, just based on our expertise. But when you add the tool, and these were all very experienced radiologists and endocrinologists, and some more than, actually many more than myself. And when we added this tool, we became significantly better, both in terms of sensitivity, specificity, and in interpretation speed. And we all became much more consistent. And so when you add this tool, it really made us a lot better. And this is something people sort of, so there's two things. This is something I would consider a clinical decision support tool. It's something that's helping you, it's not helping you detect the nodule, right? We know the nodule's there. We're not trying to find it. We just need help figuring out how to interpret it. And so it's helping you make a decision. And this is a great example of what a lot of people have referred to as augmented intelligence in radiology. So the idea that an artificial intelligence tool, there's very few artificial intelligence tools, at least currently, that could operate completely independently. And, but there's many examples where if you add those to a radiologist, the two together become much better. And so this is a great example of that. And then the last category I'll talk about, this is something I'm actually most excited about because I think it has some of the greatest potential impact. And this is the concept of radiology biomarkers or population health, or sometimes people refer to as body composition measures. And the idea here is that there's a lot of things in scans that we do that we really don't pay much attention to. And that's for a variety of different reasons. Sometimes there's just not a lot of literature describing how to do it or proving that it affects outcomes. A lot of the times it's because the people come in for other reasons. So if you have a CT, CT of the chest or the ER because you have chest pain, we may be looking for the more acute things like pulmonary emboli or pneumothorax or pneumonia or COVID or whatever, and not really paying attention to coronary artery calcifications. And then maybe the third reason, which is sort of the same thing that I already described to some extent, is that there's just tons of information in these scans. And so we have to sort of focus on the things or tailor our reports to the things that are most pertinent or most important. And it can be very difficult to go through every single possible thing that might exist in there. But there could be a really huge population health impact if we can find ways to harness that information. So this example here, you may have heard of an exam called a coronary artery calcium score, CT. So this is when patients have some degree of risk of cardiac disease. They go get a non-contrast chest CT. We draw little circles around all the calcium in the coronary arteries, and you can get a score from 0 to it can go, I'm not sure it's an upper limit, but it's very high. Anything over 100, which reflects how much coronary artery calcium is there, suggests that they're at increased risk for a cardiovascular event, and they should probably end up on a statin or some sort of intervention to prevent that. So you can see how there could be a huge impact there. It's a relatively straightforward exam, a simple measure. We know it results in bad outcomes, but there's a very cheap and easy intervention to help those people. The problem is that to do a coronary artery calcium score traditionally, we have people do what's called a gated study, and it means it's gated by ECG. And that's because the heart, of course, is always beating. So there's a lot of motion artifact that happens when you scan the heart on a routine basis. So we hook up ECG leads and we time the acquisition so it's during diastole. So the heart is relatively still, and you get a very crisp picture of the coronary arteries. But not that many people get referred for those exams, and orders of magnitude more people come in for regular CTs. So if we could somehow get that information from the regular CTs, that's a huge new pool of patients that could potentially benefit from intervention there. And what happened is Stanford developed an algorithm that basically can do that. So this is data from a non-gated routine CT, but they developed a model that can figure out where the coronary artery calcium is. And we did a big study comparing routine exams to the gated coronary artery calcium scoring scans, and showed that this model on regular exams does very, very well and almost just as good as the gated studies. And so you can see here on the left is the regular source image from the CT scan, and on the right, these little blue pixels are showing where the algorithm thinks there's coronary artery calcium. and I'll go through a little bit. You can see that it does pretty well. There's probably a few little artifacts, but mostly it's picking up the coronary artery calcium. It's smart enough to miss the aortic valve calcification, which it should not count. And so, we think it does a pretty good job here. And this came up with a coronary artery calcium score of 184. So it's over 100. This patient should probably be seen. And, because of the volume of studies where we can run this stuff, both prospectively and retrospectively, I think there'd be a huge population health impact. And so I just met with cardiology, and I'm going to present to their clinical practice council about how we want to figure out to refer these patients, basically. And they're very excited about it because they think it could really be a big benefit. And so this is a good example of where, I think some of the best AI applications are those that cross both disciplines. So we've got radiology involved and cardiology involved, and there's clinical care involved and clinical outcomes that we'll be assessing, which, to me is the most exciting. The other very similar example, this is, I'm working with a group from Wisconsin and the NIH on doing a bunch of other similar body composition metrics. So on the left, you can see we have a regular CT scan, and this is the liver here. I think you can see my mouse, but this is the liver, this organ over here. And you can see these algorithms can very accurately segment out the liver automatically. It's totally automatic, no manual intervention required. And you can use that to figure out the volume of the liver and also the fat composition. So the steatosis, which can be a metabolic problem for patients. Here you can see the liver gets segmented out pretty well. Here you can see the spleen gets segmented out pretty well. And then we also look at some other things like subcutaneous fat as well as intraperitoneal fat. And there's some other metrics and proxies you can figure out to determine the muscle mass, fat composition, and other things that can lead to adverse outcomes. And this one here is actually trying to find a number of things. It's segmenting a lot of the various structures in the abdomen, but it's also looking for the L1 vertebral body, because it turns out if you measure how dense that is, you can predict if someone has osteoporosis or not. And that's osteoporosis and compression fractures are a huge problem with a ton of morbidity, very, very expensive. So if you can identify patients that are at risk for that, you can make a huge impact on cost and patient satisfaction and morbidity and happiness. I can tell you, we actually do, look at the L1 vertebral body density manually when we read scans, but it's not done on a routine basis and not done particularly well. And if you can automate it, then that's a great, artificial intelligence application, I think. So that's all I have, but I'd be happy to answer any questions.
Thank you so much. That was really amazing. So many different applications, not only clinical, but operational, it seems like, with some of the triaging. Does anyone have any questions?
I have a question. Is there any resistance in the medical field towards using algorithms that rely on neural networks, given that they're kind of like black boxes and there's no way to really prove what they're looking at or what factors they're considering in the algorithm itself?
Yeah, so yes, I think there is some, and appropriately so. There are some ways to figure out what the algorithms are looking at by looking at different information that comes out of the neural networks that are created to produce these end images. So there are some ways to produce that. Not everyone is doing a great job of that, and even when you can produce it, the end screen clinicians don't always know what it means, and it can be confusing. So I think more work needs to be done there, but I think there are ways to help people understand like what the algorithm is looking at or what part of the image contributed to the diagnosis that it made. But the other thing is that, for the most part, and this is part of the reason why we largely see algorithms that require some level of supervision so far. If you think about the triage use case, you don't need a super accurate algorithm. You'd like it to be probably a little more sensitive and specific, but it doesn't need to be perfect, because if it tells me there's head bleeds on 8 out of 10, or on 10 scans and only 8 of them actually have bleeds, that's okay, because it picked up a bunch that I should read, and if it's wrong a couple times, who cares, right? But if you want an algorithm that actually diagnoses head bleeds and takes the radiologist completely out of the mix, you need something that's supremely sensitive, specific, and accurate with like very few, if any, failures. And that's obviously a very hard thing to achieve technically. And the FDA would require like an incredible amount of performance metrics to justify that. So So when you think about the black box problem, since we're mostly operating in the supervised means, humans are still sort of checking things in real life to make sure that it actually makes sense. So if it says there's a head bleed, or if it says there's osteoporosis, or if it says there's coronary artery calcium, we are having a cardiologist look at them and like evaluate them, and maybe even doing further studies to make sure that it really makes sense, right? Depending on the level of intervention. So I think that's how we're getting around the black box thing to some degree now, is that there's really nothing out there that's operating on an unsupervised method.
I have another question. I think it's kind of related to Alan. My question is rather technical. So when we're creating the algorithm and setting the control group, is there a certain strict protocol to follow in terms of like number of patients and diversity of patients to set up the control group in order to set the algorithm? And is there like a cutoff for the performance level to be accepted as algorithm to apply to the real patients?
Yeah, really good question, because there's not really for any of those things you suggested, which are very appropriate and intelligent suggestions, but we just haven't come up with a way to like determine how many patients, how many scans. But it's a very important thing to figure out, because these algorithms may work differently in different patients, different genders, ages, ethnicities, different locations, because of different population variances. Because of different scanners that are used, different techniques, different ways that different institutions scan their patients. And so it's an incredibly important thing, but there's no good metric that I'm aware of how many of those things you need to incorporate. The way we've and same thing with the performance characteristics. There's no strict cutoff that's appropriate for anything or any particular use case. And there are sort of generally different accepted performance metrics for different types of cases, if that makes sense, which I kind of discussed. So for triage, generally lower bar, anything supervised is going to have a lower bar because a human will be reviewing it. If we ever get to the point one day where we're really letting AI interpret scans alone, it's going to have to be very high, very good performance characteristics. So there's not a great answer to that. One thing that I've really advocated for, and I think a lot of people do, is that if you ever were to go out and consider purchasing an AI algorithm for use, you would want to come up with some way to sort of monitor it the same way you might monitor a drug or device for post-market surveillance and make sure that it's still working properly after it's been cleared by the FDA. So, you can go to some company, they say, first of all, you want to ask them for their data so they can tell you they use 100,000 scans to generate this thing, and here's our population spread, and here's the ethnicities and ages, here's the different scanners, all the different institutions, and that will give you some sense of reassurance, hopefully. But then ideally, you'd have a plan to monitor it in your practice and make sure it's still performing as well as they said it would, and come up with a plan to remedy that if there's any problems.
Thank you both, Dr. Filice and Dr. Shara, for your amazing and very informative presentations. So I kind of have like a more big question, like that I'm very curious to hear about from the perspective of both a statistician and a clinician. So both of your presentations have definitely been centralized about how important data really is. And a lot of very important and clinically useful data comes from EHRs. And unfortunately, EHRs aren't very universally accessible. You need to get a lot of permissions and whatnot. And so how do you guys feel, / do you see any direction for the integration of EHR and blockchain technology in order to make data from EHR not only anonymous, but also universally accessible for researchers and pharmaceutical companies alike?
So I'll take a quick stab at this. There are lots of efforts, right, from NIH specifically that's trying very hard to democratize data by funding to enable the share of data, such as all of us and 3C. There are lots of available data that's out there that ensures the participation of all kinds of people's data into it. That's one. And I think that's an excellent question. I don't know about the blockchain or the quantum computing or whatever. I don't think it's a problem of technology. I think it's a problem of trust, problem of diversity and so forth. And as Ross alluded to, the data that you put will determine the performance of the tools. So these are my 2 cents on this space. and I'm working so hard on addressing the trust and the ethical issues on the development of the AI tools, and data is a major part in it.
Yeah, I mean, I would very briefly just generally agree that it's not a technology problem. It's figuring out the, bureaucratic and legal things to make sure privacy is protected where appropriate and making it available. There's also been not a lot of great work with standardization of data. There's been some standardization of methods to acquire data. So we use the FHIR standard here to get some data from EHR, but the way it comes back isn't necessarily standardized, certainly not across vendors and even across different implementations of institutions with the same vendor. So that's a difficult thing to address.
Thank you for that question, Kabir. And thank you again, Dr. Filice and Dr. Shara. I may just share your contact information with the people if they have any interest in reaching out, if that's okay with you. We're going to have a short raffle at the very end. So feel free, if you want to stay, Dr. Filice, Dr. Shara, you can, but we're just going to have a short raffle. And after that, we'll kind of conclude. So I'll give it over to Angela, who's our president, and she'll kind of do the raffle.
I'm assuming we're not part of the raffle. I'll sign off to you guys.
If you would like to join, I can.
No, it's fine.
Have a wonderful
Enjoy.
day. It's a pleasure meeting you. Your questions were very, very insightful. Thank you.
Yeah, thanks for having us.
Thank you so
Thank you.
much.
Thank you, everybody.